That's how we choose the basis, because it's the most convenient, most obvious way. So therefore the trivial product, of course, is the exterior product. So this thing is already associated with the plane spanned by the two vectors. If we go further, we have in 3 dimensions nothing more than a 3 vector. We cannot go further because obviously the flow volume of 3 dimensions is 0. This is a volume element, or as we call it, this is the highest grade, as we call it the pseudoscalar. So apart from the scalar, we have a pseudoscalar. So the other thing which is 1 dimensional, the other thing which is 1 dimensional, is spanned by the volume element. Okay? This is E1, E2, E3. The determinant is like the matrix algebra, is the determinant of the mixed product of the triple product. Okay? So let's see how these things work. If we want to consider the triple algebra let's construct this from scratch. So we have 3 unit vectors. Right? And we have this condition that it was like the current of yeah, actually, this already tells you everything. So you have to know more basis. And then what are these going to be? Well, as Professor Gonzalez explained, these are the quaternions. So if we take only the even grade algebra, it's usually denoted by this. These are the quaternions, which are, maybe I should have written first in trivial representation. 0, 2, which is one of the very few Kubit's algebra, one of the very few non-division algebras. We only have a couple of those. You have the units, you have the complex, you have the quaternions, and of course you have the quaternions, which are not associative. So this is although it has to do something with different algebra and classical groups, this is not a different algebra, but those ones are. And you have you're not, okay, if you want to preserve invertibility, the division property, you're fixed to this path. Okay? This is the system of the development process, but you can make different generalizations. Okay? For example, instead of the complex numbers, the so-called hyperbolic or split complex numbers, also denoted by. Here you also have, for example, the big complex numbers, or you have the split quaternions. Okay? Here you also have other options. For example, you have the biquaternions, complexification. These are all different algebra, so everything without this one is a different algebra. So it's good to follow a path starting from the simplest thing. So it's very easy if you have the complex numbers to isolate the real components and say, okay, this is some sort of continuation of ij and k for a given all three of them square to minus 1. And of course they have this beautiful multiplication table. Ij equal k, ik square. Wait, the way I've written those, is going to be, there's going to be one minus. There's going to be one minus. Because they use the notation, the convention is that we order the indices.
The expression I have written before application, written with I job k must change.
Yeah.
Quaternion and the English quaternion for because of there is a change of sign between
This is the same object, but it depends on the perspective from which you look at it. If you look from the three-dimensional perspective, you have to be careful. If you want to look from the two-dimensional perspective, so forget that there is a three-dimensional space. You can think that we only have two-dimensional space, but the squares of vectors are negative. Okay? So this is the trivial algebra. This notation again. This notation means that there's a metric which defines the different algebra. But in the form with 0 pluses and 2 minuses. Okay? So the orthonormal basis would be with minus 0. And if you start from here, you have two vectors, I which squares to minus 1, of course, j which squares to minus 1, and this is a pseudo-scalar. This is the volume form, is a two-vector because you have two-dimensional space. And it's not difficult to see that it also squares to minus 1. We call this k, okay? Because it's just the next letter graph. But anyway, one should be careful with the definitions, but still, this is the same algebra. It is a sub-algebra because what Professor Vargas said is a particular property of a different algebra. You have a Z2 gradient, so you have the even and odd grades. You don't have the gradient which you know polynomials have. Something is either even or odd. But if you multiply two odd things, you get the even thing. So this is not a sub-algebra. But for even grades, it's the cost of the multiplication. So you have your quaternions embedded. Okay? So if you want to start with quaternions, the way you construct complex numbers from reals and quaternions from complex numbers, right? So quaternion can be written as G1 plus, well, let's say plus double J. When Z and double are complex numbers. So it's pretty much, it's very similar to the construction of complex from reals. Okay, so if you want to go from here, from knowing quaternions, you construct the whole space algebra, just three-dimensional space algebra. What do you have to do? It's something similar. You have two quaternions, let's say Z and W, okay? Now they're going to be quaternions. And you want your elements. How should I call this thing? Maybe big letter I. You want this to be a representative of the space algebra. Okay. What would this thing be? It's an analog of the imaginary unit, right? It's an analog of the imaginary unit. You extend your the whole equation. But it turns out it is the very imaginary unit because this is actually the so-called pseudo-scalar. It has this very nice property that it squares to -1. And it commutes with all elements of the algebra. So it has the very algebraic property of the definition of the imaginary unit. So you can actually, okay, it's not nice because I used IJK following Hamilton, but okay, this I would be different I. But this I is the imaginary unit. So it turns out just as an algebra, this is just a complexification of the determinants. Okay? And if you want to follow this process from two-dimensional to three-dimensional algebra, two-dimensional space to three-dimensional space, the next one will be the one of space-time. So if you want to continue with this, so you have the quaternions, which I'm going to write in different algebra positions, which are the given dimensional subalgebra of the three-dimensional one. Okay. So the next one would be space-time. Okay. 3-1 or 1-3, they are different algebra, but this embedding is true in both cases. In terms of the even subalgebra, there is no difference. So, but this is for the next lecture. This is how you construct isometries in some space from the even subalgebra. Okay, this is for the next lecture. But now, how do you construct isometries from quaternions? How do you construct rotation from quaternions? I think it's very popular. Okay, just I'll show the formula. You have so some people would say the -1 is good if you have invertibility. Some people would just use some sort of evolution. It's usually actually the composition of two evolutions. Anyway, it's what Professor Gonzalez explained, that if you take an arbitrary element, okay, so say a vector, it would be a reflection. If you take two vectors, this is a combination of two reflections, which gives you a rotation. So that's how we rotate with quaternions. In this case, of quaternions, it's a division algebraic branch into the -1. It's a very standard procedure. So from the even dimension of subalgebra, you get the group of isometries. Now, after we do the same thing in space-time. We get the Lorentz group, not from the space-time algebra, but from the space algebra, because we don't need to call. Okay, sorry, I just wanted to repeat some of what you said on the board. Time to.
Yes, it's time to have
lunch.
Yes.
Yes.
Yeah, I was remembering that when you have like quaternions, you can. It's easier like to. I don't remember if you remember. You do a triangle. You put A, J, K, and you make some like.
Because it's secret. Yes. Because it's secret, the composition with J equal K with N and so on. In the reverse direction, it would be minus sign involved. Is that what you mean?
Yes. Also, is that I was remembering how to make operations with quaternions easier, because I was remembering a triangle and we compose like one side with another. One vertex of a triangle with another, and they give you the other. I don't remember how it works, but
I'm not sure I'm thinking
The
of
composition of quaternions.
yes.
Es como diente.
Yes, yes.
I know. Yes, if you.
You can compose geometrically quaternions. Each quaternion is a fusion of vectors. So you have here fusion of vectors and another fusion of other vectors. But the places are not always different places in general. You can relate if you have the intersection of planes. You can relate in the angle up to join this vector with this. Okay? And then the result, if both vectors have the same image, is the mean triangle form by this vector. This is the composition geometrical from the geometrical point of view. Okay? So we have data about triangles. And then this new triangle with this new plane is then something like that, but taking into account the problem of the norms. It wants to be the same, because if the norm of the vector is the same, then there is a fastness or a shortening of the. And the cushion of the vectors is the new quaternion, the plane of the quaternion, or the resulting quaternion. The plane is the plane of. You must rotate and join one side of both. One of the vectors, one side of the triangle, you see. Okay? This is explained just by how this explain all this in the elements of quaternions, 19th century. 1868, I believe, is a posthumous book. Written after his death. Okay. But he wrote the most part, and he had already published books. The lectures of quaternions are from some years before his death. First the lectures and later the elements. But this is explained by him.
I wonder whether any of you can give me a good reason to do quaternions. Because one can do everything quaternion, having to do what quaternion just use the triple algebra of 3 dimensions and period, and forget about quaternions because.
No, quaternions are only for notations.
No, not necessarily. Yes, you need with quaternion that is more complicated. I can do rotations, okay, in 2 lines without mentioning quaternions at all. Okay, do the product of 2.
You are saying that a quaternion is a product of the 2 direction vectors of our axial symmetries. It's the same.
Yes, I know, but what I'm saying, there is no need to start thinking, okay, I'm going to relate the quaternion. To start with, in the quaternionic algebra, in the original Hampton, there was 1 on the one side, okay, then I, J, K, and don't together, they were at pi. Okay? And in reality, it is the triple algebra of 2 dimensions. Well, I and J, okay, are bivectors, probably are vectors, and the K is a bivector. The bivector.
This is an iterative way to construct.
Okay, and and rotations into lines without mentioning dimensions.
They are very good for the Campo lecture because he considers only two-dimension surface of two-dimension, and for two-dimension this Hamilton algebra is perfect. So this is really help to the Campo lecture. It's just only surface. It's only surface.
Yes,
The surface is only Hamilton.
yeah, but in the surface you only have I and J.
But
And the K is the stereo product of like J.
this is what the Campo has in his lecture. But he never mentioned dimension. But he has dimension too.
Okay, may I just add something? Because I'm a very important. It's just a name, but it's just one of the many different algebras.
At 5 o'clock I challenge you. You do rotations on the left, using quaternion to define a quaternion and so on. Assuming we know Greek algebra, okay? And I'll give you 50% advantage. I'll do it in half the stage you're going to do it.
Shall we have people betting? Shall we have bets?
Should we have one?
Bets.
Bets.
Big money.
People betting men.
Put it down your money.
Okay, otherwise I don't do it.
That's all.